Alright, guys. Kind of weird here doing a video of a lesson instead of being in front of y'all. Um, but here goes. This one's a really quick lesson. We give you some work to do on it. But look for another lesson coming up this week um, shortly to do some more work because this is not going to take very long. Alright, Euler's method. Alright, if you remember from when we were pre-spring break, and we thought we were all coming back in a week. We were talking about differential equations. All right, differential equations are equations where we have a dy dx. Okay, we have a slope equation. All right, and sometimes those could be really easy, and we know the derivative is x squared, and we did that when we talked about antiderivatives. We could find the antiderivative of that really quickly and find a family of equations that had this as their derivative. Okay, and we had the plus c because we didn't know exactly where that function actually started, because all of the functions, all of the 1/3 x cubed functions have the same derivative. Okay, so their slope fields would all look the same. Or the slopes would all be the same at particular x values, but it all depended upon the plus c where the function started. Okay, and if you're given a slope field, a lot of times we'll say, hey, with the initial condition that maybe at 0, I'm at 1. So maybe our initial condition is y of 0 is equal to 1. All right, and then draw that curve or figure out what the answer to this differential equation is. All right, it looks like this dy dx is probably a negative sine x. I just pulled this one up just for visual purposes. All right, we can actually do this the old school method. But sometimes on the AP test, we'll say, hey, this is a slope field. Draw the solution curve. All right, and so what you do is you just follow the curves. Okay, you go, hey, right here, we're kind of sloping here. It gets less steep. It looks like it's flattening out and coming back up. Maybe going this way. Looks like it's kind of getting steep, but less steep. Now it's 0 and coming back down. All right, we could draw that function. Okay. Sometimes our differential equations have both x and y in them. All right, and we talked about before spring break using separable differential equations to bring the y's to one side, leave the x's on the other, and do two antiderivatives and solve that out. All right, but sometimes those differential equation is not separable. For example, dy dx is equal to x plus y. All right, you might think this one's separable, that you can separate the x and the y's. And you can bring the y to the left-hand side, but you can't split up the dy dx nicely, okay? Because if you brought the dx over here, multiplied it over, it would go to the x and the y, and I couldn't just bring the y over, I'd have to bring the dx back over as well. All right, and so what Leonard Euler, famous mathematician, his method was, you know what, if I want to approximate a curve, okay, I'm going to use an iterative method. All right, and it's basically the tangent line approximation. Okay, if I know what the slope is, which is that's the dy dx, and I have an initial condition, say y of 0 is equal to 1, I can find the tangent line at that 0, 1. Okay, and I can draw that. So over here, I could draw the slope right here. Let's say that slope looks like maybe a negative 1. All right, but that line there, if I extend it out, that's a horrible approximation for that curve. Okay, and so what Euler said, hey, instead of going the whole distance out and saying that curve is there universally, let's go out just a short distance. Okay, let's just go out just a tiny bit, find out what the, we'd have a new y value there and a new x value, and plug it back in. So maybe our curve at a half would come out and do like this. All right, and then find out what happens at 1. Find a new slope, which we'd have a new y value that we got from the previous one, and draw that tangent line. So maybe that tangent line goes like this. And then do it again. It gives me a better approximation of that curve than just doing a single tangent line. And so here it is written out in this nice fancy math talk. It says y of n plus 1. So the next y value is what you get when you have the initial y value, or the y value you have currently, plus the derivative at the particular x and y value you are right now, times your delta x. And we're going to call that step size. All right, that's how far you're going between the starting point and the next point. Okay, and you do that for how many ever steps you have. All right, and so if you notice here, that's kind of like the tangent line approximation. Okay, your y sub n is your y sub 1, but that'll change for each step. Your m tan, that's your derivative. All right, and then the delta x is simply, hey, the x I'm at minus the x I was at previously. So that's your change in x, or your step size. This is a change in x, a delta x. All right, and so I say here we're approximating a curve. What we really do is we're trying to find values of a function. All right, so let's look at an example. Let y of x be a particular solution to the differential equation dy dx is equal to x plus y, with initial condition that f or y of 0 is equal to 1. Use Euler's method with 2 steps of equal size to approximate f of 1. Okay, so I don't know what the actual function is. Okay, but I do know that at 0 the function's 1, and I want to know what the function is when x is 1. All right, and we want to use 2 steps of equal size. All right, so look at where you started at. I'm starting at 0, and I'm going to 1. So my delta x would be 1 minus 0 over the number of steps, which is 2. So my step size, my delta x, is equal to 1/2. All right, so here's how I would work it out. I'd have y sub 1. Okay, this is the first step. All right, it would be my y sub 0. So what is the y value at 0? It's 1. That's my y sub 0. Plus my delta x, or excuse me, my dy dx, so that's my slope, my dy dx at the point 0, 1. All right, so if you plug 0 and 1, here's your x sub 0 and your y sub 0. So that would be 0 plus 1. So my slope is 1. And then I'm going to multiply that by my delta x, my step size. So times 1/2. And so if you work that out, 1 plus 1/2 would give you 3/2. All right, so that is your y sub 1. And so for the next step, we're going to use the fact that, hey, I was at 0, 1. All right, and now that I moved an x value of 1/2, I'm up at 3/2. Okay, so here's I'm trying to get to at 1. At 1/2, though, I'm at 3/2. So I got x value of 1/2, y value of 3/2. And then my y sub 2, my second step, my y sub 2 is my y that I got from the previous step, which is 3/2, plus my derivative at this point, 1/2, 3/2. So 1/2 plus 3/2 is 4/2, so that gives me 2. Times my delta x, which my delta x stays the same every time, it's 1/2. So that'll be 1/2 plus 1, so that would give me 5 halves. All right, so that tells me I went another 1/2 step, so my new x value is 1, and my y value there is 5 halves. So our approximation is that f of 1, the value of this function at 1, is approximately 5 halves by using Euler's method with 2 steps. Okay? That is Euler's method. We'll do just one more example for you, and then I'm going to put you some work on Canvas to look at. All right, consider the differential equation dy dx is equal to x squared plus y. Particular solution where the y value at an x value of 2, so your x sub 0, y sub 0, is negative 1. And I want to approximate y sub 4 using 4 steps of equal size. So I'm going from x value of 2 to x value of 4 using 4 steps. So my delta x would be 4 minus 2 over 4. And so this turns up on this one, my delta x is still 1/2. All right, so we have 4 steps. Step 1, y sub 1 is going to be my initial y value of negative 1 plus my derivative at 2 negative 1. So negative 1 squared is 1 plus 2 would give me 3. I'll go ahead and write that out here. Negative 1 squared plus 2 times my delta x, which is 1/2. So that gives me 3 times 1/2 gives me 3 halves. So negative 1 plus 3 halves gives me 1/2. So right now, my x value is 1/2 away from 2. So that's 2.5 or 5 halves. And my y value is 1/2, if I've done that correct. 3 halves, which is 1.5, yes. All right, step 2, y sub 2. It's my new y value, which is 1/2, plus my derivative at my new point, 5 halves, 1/2, so that would be 25 fourths plus 1/2, which I'll go ahead and write as 2 fourths, times 1/2. All right, add those together. That gives me 27 over 4 times 1/2 gives me 27 over 8 plus the 1/2, which is 4/8. So 27 plus 4 is 31 eighths. 27 over 8, 4 over 8, 31 eighths. So 5 halves plus another half gets me up to 6 halves, or 3. My y value is 31 over 8. All right, and remember, we're trying to figure out what is the y value when x is 4. So we have 2 more steps to do. Y sub 3, our new y value of 31 over 8, plus our delta or dy dx at 31 over 8. So give me 9 plus 31 over 8 times 1/2. All right, 9 would be what? 72. 9 times 8 is 72 over 8. So 72 plus 31 would give me 103. 31 over 8 plus 103 over 16. I'll multiply by 2 on top and bottom here. That gives me 62. So I have 165 over 16. If I'm making some stupid mistakes here, just laugh at me and you can rag on me later. So my new point, if I add 1/2 to 3, that gives me 3.5 or 7 halves. And 165 over 16 is my new y value. So we got one more step to get there, our fourth step, because it told us to do 4 steps, and it will tell you the number of steps. Y sub 4. Our new y value, 165 over 16, plus our dy dx at the 7 halves, 165 over 16. 7 halves squared is 49 over 4, plus the 165 over 16, times our delta x, our step size, which is a half. Oh, and now we got to do all that arithmetic. So we got 165 over 16. All right, if I multiply by 4, 4 times 9 is 36. Go ahead and write this out. So 4 times 4 is 16. So 196 over 16 plus 165 over 16 times 1/2. All right, that's going to end up being 32. So if we multiply that by 2, 65 and 65 is 130. So 330 over 32 plus, so now this is going to be a 32 on the bottom, plus 361 over 32. When I add those two together, and so that ends up giving us 691 over 32. Okay, and so that would be the point. 1/2 away from 7 halves, so 8 halves are 4, 691 over 32. So y of 4 would be approximately 691 over 32. All right, and you can tell that if your dy dx is not really simple and you have more than 2 step sizes, this gets out of hand pretty quickly. And so most of the time, if you see one of these on the AP test, it's usually maybe 2, maybe 4 steps. And they do it where it's not too bad arithmetic. All right, y'all try those problems so that you have questions to ask. I'm looking at possibly setting up some kind of meeting on Wednesday to get together with y'all to answer questions you might have on this or on your previous assignments. I will see you then. Stay safe